Okay, so in this reflection is not that much important. You can say recall. We are going to start from the recall, like the basics, difference between DC and AC, and then the things what we are need to discuss in this. So DC, we everyone know, if a circuit contains a battery and a resistance in a series, then EMF and the current in the circuit are as shown below and known as a direct EMF and direct current. Magnitude of EMF and current does not vary with time in DC circuits. So that is your DC EMF, or you can say voltage, and that is your DC current. It is not going to be vary with time, whatever the frequency is going to be. So frequency is not going to be changed, it is going to be zero because it is not vary as the alternating EMF or alternating voltage or alternating current is going to be moving or changing. Is this clear, everyone? So that is basic thing. Now alternating EMF. So quickly recalling this thing. Magnitude of EMF or voltage changes continuously with time between 0 and maximum value, and also direction reversely, you can say also direction reverse periodically. Like as you can see, this is going to be the maximum point. Wait, so if it is, yeah, so the maximum point is going to be this one, and this is the correct, yeah, this is going to be your maximum EMF or peak voltage in positive direction, and this one is going to be maximum or peak voltage in negative direction. Okay, so this kind of EMF and this kind of current is basically known as alternating EMF or alternating voltage or current. A sinusoidal alternating EMF is developed in a coil of wire rotating with a constant angular velocity omega in a uniform magnetic field. The magnitude of the alternating EMF changes with the time and its direction reverse periodically as shown in the figure. So this omega t, this is your in general omega t or simply t, and this omega is nothing but angular frequency 2 pi f. Okay, 2 pi f, or in general it is what, whenever a coil is going to be rotated, so this omega is the rotating velocity also. Clear, everyone? Is this clear now? That's we already done. And the students who join this class, please turn on their cameras. So this is your alternating EMF, and this is the important thing, because from this particular single equation we are going to derive everything, and we already derived the things in the previous lecture. So taking it as a general equation, or you can say equation 1, or you can say GE, any general equation for alternating EMF, okay, or voltage, you can write it down also. The moment we divided with the, you can say the moment we apply this kind of EMF or voltage in any particular kind of circuit, so basically the current is going to be generated, and that particular kind of current which is dependent on this omega and t and sine, and so you can say sinusoidal, that is known as your alternating current. Okay, here E is the instantaneous value of EMF. This E, what is this instantaneous means? At any particular instant of time. Okay, suppose you want to find at any, I mean at the time duration 2 seconds, at the time 4 seconds, 5 seconds, n second, any particular single duration. So that is why it is given the name of as a instantaneous. E naught is the maximum or peak value. I already defined this so many times. This E naught is your maximum or peak value. Either you can write maximum, okay, or either you can write peak value. Peak value. Is this clear? Omega is angular speed of the coil. Omega t is the phase of alternating EMF. Omega t we also define. Omega is angular speed of the coil. Clear everything? Is this clear or not? Just type it yes if it is clear, so I can move ahead, right? Because seeing you sitting like this, I don't think you have a question, query or not. Yeah, form factor. This is very, very important and it is going to be asked directly. Or you can say very important. Mhm. Okay, so form factor, what is the meaning of form factor? First of all, RMS value of an AC divided by the mean value of AC over half cycle. Why half cycle? Because we know the mean value of AC, alternating current, alternating voltage over a complete cycle is going to be 0. Clear? So as you can see, form factor is not dependent on anything, but it is in general important. Why so? Can anyone tell me? Have you ever been thought like why always you can see that the alternating voltage or current is the multiplication of 11, like 11,000, 1100, 22,000, 2200, 220 volt, 110 milliampere. Why so? What is the reason behind that? Anyone know about it? Anyone? So this is the reason, form factor. Okay, so RMS value over of AC divided by the mean value of AC over half cycle is going to give you the form factor, and basically form factor for sinusoidal AC, because whatever we find, one thing, okay, I want to discuss one thing important also. Tell me what is the average value, even it is written over here. RMS value is, you can say RMS. Okay, please anyone tell me what is RMS and why we require that. RMS value of AC. Anyone please. I define separately and it is important too. It is I naught by root 2, right? Or another thing, average or mean value. Average or mean. Tell me beta what is RMS? Anyone? It seems so easy, but when you are going to define it is not that much easy even. Average or mean value of AC for half cycle. For half. What happened to my writing today? For half cycle is this. What is this? 2 naught upon pi. Tell me what is RMS value. You can speak up also instead of writing. Sudarshan, Shrutika, Parikshit, Kyle, Netra, and Vishwanath. You don't need to write every time. Are beta, I know. RMS, I mean full form, I know. Why we require this? What is this in general? I'm asking this. I know RMS means root mean value, sir. Seriously, I'm going to ask this much easy. I know this thing what is. I mean, what is root mean value? Why we, or root mean value isn't it the correct thing? Root mean is square value. I write RMS, not RMV. You tell me, Shrutika beta, why we require this RMS value? Tell me. See, that is missing in the previous class, so that is why I generally deliberately given to you. And that is important too. If you don't know why we require this RMS value, so believe me, you don't even know the beginning or basic of AC. Tell me, are you there? Tell me why we require RMS value. What is the basic need? Or anyone else, if you want to. And try to speak up instead of writing. Because whenever I'm seeing to you guys, I don't, I mean, I'm not able to read on the chat because I'm watching you guys. And I don't know why you have I mean that fear, or I don't think so, whatever the thing is. See, the basic thing, RMS, root mean square value, because we need to take some steady value to count on as a DC, right? And we know this thing for complete cycle, the average value or the mean value is going to be 0. And because we know our general equation for current is going to be, either you can write I naught or either you can write IM, maximum or peak value, sine omega t, right? So this is my instantaneous value. Clear? This equation number 2 or equation number B is my instantaneous value of current. For any particular time duration, I need to find the average. Suppose I have I1, I2, I3, I4, dash, 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 I10. What is this? I am going to find the current at 1 second, 2 second, 3 second, 4 second, 5 second, 6 second, 7 second, 8 second, and so 10 second. So what is the average value? For complete cycle, it is going to be 0, right? But obviously, alternating current is going to be measured for complete cycle, because it is not like, sir, it is going to be 0, so we are not going to find a solution. So we can find the complete cycle. It is not going to be the, so for that reason, we find root mean square value. And what is the need? What is the basic thing? Because the moment I do the root, so this is my positive cycle, this is my negative cycle, positive cycle, negative, positive, negative. Even negative cycle is going to give me the positive magnitude. So I don't need to worry about the magnitude at that particular moment. Suppose at 3 second, my instantaneous value of current is this one. At first it is this, at second it is this. Even at fourth it is this. So I'm not going to deduct, I'm not going to, you can say, remove this I3, I4 value. The moment I square that, automatically I can get the mean or average for full cycle. And obviously if I'm squaring, so I need to do the, you can say, root square also. So it is basically, in general, the average or steady or mean value for complete cycle. Got it or not? Is this clear, everyone? And that is the very basic thing. I don't know, you don't understand in the last lecture, and I want to ask in the last, but I think I'm going to ask in the next. And I know most of the student doesn't understand what is happening here. Believe me, I mean, that is not going to be tell you the thing, but in Viva, in interviews, in demos, 6 out of 10 teachers also don't able to explain this. So I'm not amazed that you don't know. It's okay. Got it? I'm saying 6 out of 10, 60%. Even they teach so many times, even they know everything. You can say the formula, the content, the everything, but the basic thing is always the difficult thing. That is the problem. So write somewhere in your notes to get the average value, mean value for complete cycle. Why we need average or mean value? To count as a steady value. And why we doing so? I mean, that much hard work, because you have to pay the electricity bill. If you are going to find the average value for complete cycle, so electricity bill without this thing is 0. Government is going to be dump, isn't it? How much they earn money with the electricity in this way. That's why we're doing this that much, because everything is related to money at the end. Got it? Suppose if the engineers, if that particular physicists don't find this, so every month you got the 0, because at the end the average value is 0. But it is not. You use that particular electric current, alternating current in your home. You run the all particular appliances right now. Without electricity, nowadays in rural areas also, or in urban areas or middle town also, we can't live 2 days. Right? because water, electric heater, fridge, fan, everything is running with this electricity. Got it? So that is why it is most important thing. It seems so easy, but it is not in general. So form factor for now, why I should repeat this everything? Because this I naught by root 2 or 2I by pi is only and only for sinusoidal. If I change my AC na, if I do this sawtooth, okay, what is a sawtooth? In the previous class we see this thing kind of. For this particular kind, the I average is not equal to 2I naught by pi, neither IRMS is going to be, it is not also. So it is applicable for this only. The method is going to be remain the same. Go to the previous class, how we find that. Simply whatever the function. Obviously, I don't give you the function for this. So you cannot find it in this way, right? Clear na? I average is simple thing. Because we find for half cycle. So, okay. Suppose the function is for I sawtooth. It is going to be I naught exponential e to the power omega t minus 1. In this way, I'm just giving you one example. Sawtooth is some different function. Even right now, I'm not remember. So you need to do this exponential. If I write it down, so I can do this also. dt. You need to do the integration and so everything, and then put it in the value and the upper limit or lower limit also. Is this clear? Is this understood? But I'm doing here, whatever the function for any particular thing is given to you for any particular different kind of other than sinusoidal or cosine. Clear? So you need to put into the same formula and do the integration. Clear everyone? The method is remaining same. The general equation, the initial equation for alternating EMF, alternating current is going to be chosen as per the given kind of format or representation. In the previous class, I told you, I think 4 or 5, 6 maybe, right? Sinusoidal, triangular, square, sawtooth. So in this way, whatever the method, sometimes, generally, deliberately, to make any particular question hard, they don't give you this. They deliberately give you this even with this kind of equation, general equation, and find I average and I RMS. And most of the student, I can say 85% student write directly this. And that is why it is clearly mentioned for sinusoidal AC. Okay. For sinusoidal AC, form factor is this. For another kind of AC, for another kind of alternating current, the form factor is going to be changed. Obviously, it is going to be changed because the general meaning of form factor is sorry, RMS value of alternating current divided by the mean value of alternating current or EMF over half cycle. Is this clear? Are you clear why I'm stating everything again and again? Because it is important. Directly they give another kind of alternating current in the equation, obviously, like square one. And they find and they ask form factor. And believe me, the form factor, everyone is going to write this one. And they obviously give you this, you can say either a multiple choice MCQ, this one, or if they ask, you can say the numerical, this you can say theoretical question. So maximum number of times students write this. Clear everyone? The main thing is RMS value of AC is root mean square value to find the average or mean value over the entire full cycle. First thing. Second thing, the form factor is the ratio of RMS value to the average or mean value of half cycle. And the cycle and the kind of a general equation for any particular alternating current or alternating voltage can be different. We already discussed this thing in the previous class. Clear na? Pavan Aditya. Beta, are you new in this class? I can see you first time. Pavan Aditya. You can speak up. Are you new? You are not audible. Refresh and then try to speak up. Yeah. Refresh this and then enable your audio. Is this clear, everyone? Why we are doing this and what is the importance of this? So these are important too. Not only for class purpose, but for in general also. Suppose you learn every particular thing related to EMI and AC and someone asks why we use RMS. So what you are going to say? Just because of topic, just because of formula, just because of this thing. And then they are going to laugh if they know so. Right? Suppose you're a younger student, I mean a younger, you can say, not colleague, but younger class fellow or brother or sister, after you passing this particular class 12th and they are in 10th or somewhere, they ask in this way, sir, I mean bhaiya and didi, like AC is going to be in this way, so the average value is 0. So how we get the current bill or electricity bill? So what you are going to say? We don't know. See, that is the beauty and that is the hardest thing. In the same way, one of my examiner asked me the question, and that is very lame and basic. The answer is very difficult. Thank God I don't have younger sister or brother. But you have younger students also, na beta? Isn't it? Suppose any one of your neighbor or neighborhood relative cousins, they are doing something in their education, isn't it? Or you are the youngest in your entire surrounding or known thing. Then it's okay. We done this. Okay. So series LCR circuit, very important for theoretical wise or for you can say MCQs only. In most of the electrical components which is going to be used or which are going to be used by alternating, which they use alternating current or EMF or voltage in that particular scenario. Have you ever opened any particular circuit? What is circuit now? Like there is a green color belt or there's a green color plate you've seen in any particular instrument right now. Phone or you can say remote or everything. Yeah, exactly. Even in smart watches everywhere right now. So basically there we use uh, not L in general, but C or R deliberately. Because L is taking scene servants. My father broken the remote. You can do that also sometime. I mean, if the remote is not working, broke that thing. Simple. Be curious enough to do something which makes your parents not proud to you, but you understand the real beauty or real thing about science. So, okay, I only fixed and it worked. Nice. So what happened? L is, you can say, inductor is basically used in heavy devices or in particular kind of components in which great amount of electricity, great amount of or you can say higher amount of electric current is going to be used. But C or R is going to be capacitor in general or resistor in general is going to be you are able to see that and in a particular small electric component like remote or mobile or anything, or you can say the motherboard or this IC, basically they known as integrated circuit of your laptop, PC, anything. Okay, so in general what is happening there, this combination is going to provide the kind of a voltage, because C is going to store the voltage, okay, and R is going to run the current. So basically what happened, uh, adapter is very small thing. Whenever you charge any particular thing, so there is a adapter, right? Without adapter you cannot charge. So what is happening in an adapter, alternating current is going to become, and that is going to be stored here, C, and then this RC circuit convert that particular, with the help of diode, convert that particular you can say alternating current into the direct current, and then it is going to be stored in any particular form of uh, you can say your smartwatch or your earbuds or your phone or your laptop and smart, you can say tablet, anything. So there is a RC circuit. L is not going to be. Okay. This is going to be the practical use. An LCR circuit, now coming back to the topic. An LCR circuit is made up of three components: an inductor L, a capacitor C, and a resistor R. A tuned or resonant circuit is another name for it. A series LCR circuit is made up of these devices that are connected in series. As a result, the resistor, capacitor, and inductor will have the same amount of current flowing through them. Basic understanding and basic knowledge: whenever any particular components is connected into the series, so they same, and the current is going to be the same. The voltage is going to be divided. Or in parallel circuit, the voltage is going to be remain the same thing, but the current is going to be divided. Is this basic thing everyone know, or everyone should know till now? Is this clear? Clear na? And on the basis of that, we can find R total, if you understand and if you know. Clear? So that is very. Now, derivation of AC voltage applied across series LCR circuit means how much voltage is going to be divided, because obviously voltage is going to be divided into three cases. If it is a V, total V, so VL, VC, VR, how much voltage is going to be on the particular component, on L, on C, or on R. This is your first component, this is your second, this is your third. Is this clear? Clear na? So an inductor L, capacitor C, and resistors R are linked in the series in electric circuit, which is powered by AC voltage. Okay, fair enough. The alternating voltage V supplied by the voltage source, where V equals to Vm sin omega t, where Vm is the amplitude of the applied voltage and omega is the frequency of the applied voltage. Clear enough? We apply alternating EMF or a voltage into that particular kind of circuit, and we want to discuss, we want to find this different, or you can say voltage dividation or voltages at particular circuit, at particular component, not circuit, at particular inductor, capacitor, and resistor. Clear? Good. So net EMF across the circuit, V source voltage, voltage drop across the resistor, voltage drop across the capacitor, and self-induced EMF in the inductor, Faraday's EMF. Why we are, is this clear not till now? What is happening here? This voltage is going to be divided. Obviously, it is going to be, because it is in, the circuit is series circuit. So here we get the EMF voltage, because whenever the current is passing through that, so there is a EMF or inductance process going to be done, and due to the inductance process, there is induced EMF. Induced EMF E is going to be minus L di by dt. Clear? You know this thing from the previous chapter. We take care, or we carry this thing. Good. And simply on this particular R, we everyone know using Ohm's law, IR. And this one is very easy even. You can say charge on this is CV, so voltage on capacitor. Voltage on capacitor is charge upon capacitance. And how we know the charge? We know the charge which is induced, or you can say which is this particular charge is coming from I, which is dq by dt. So q is I dt integration. Clear? So in this way we can find every particular voltage, or you can say voltage on every particular component. Is this clear, everyone? Please let me know. Clear na, everyone? We are not doing anything new till now. So the new thing is we are going to find the different kind of voltage on different components. Simple. So V net voltage is L di by dt, IR plus QC, Q divided by C, substituting an alternating voltage for the expression V equals to Vm sin omega t, L di by dt plus IR Q by C. This is your equation number 1. Going ahead, we know that the current is equal to the rate of at which the electric charge flows per unit time, that is I equals to dq by dt. So differentiating both sides with respect to time, we get di by dt equals to d square q upon dt square. Clear? So now we have di by dt and we have I also. We put everything into the form of q. Clear? Till now, till equation what we are trying to do, we are just rearranging, or you can say writing this equation 1 into the form of q instead of I, because q is the basic quantity, charge is the basic quantity. Clear? Or alternating charge is, this one is. Okay, good. So now the equation for a forced or damped harmonic oscillator is similar to this equation. Now in the previous class we understood, I'm saying correctly. In the previous class, we understood two types of SHM, or you can say oscillator, harmonic oscillator. Simple harmonic oscillator or damped harmonic oscillator. Damped harmonic oscillator are those oscillator in which we apply some internal frequency and there is going to be damping. Damping is going to be, so why and how damping is going to be work, if you don't remember right now. So in SHM, okay, in simple harmonic motion, what is the case? The frequency is going to be in this way, simply, if it is cos value. Okay, but in damp value, but in damping value, it is going to start from this, in this, in that, in this. Clear? It is going to be damp. Damp means it is going to be and, because there is a force fully and then there is damping applying that. Clear, everyone? If you don't, just go through a little bit from the previous class, 11th class oscillator thing. The equation for a forced damped harmonic oscillator is similar to this equation. This equation number 2. This is your damping. Okay. This is your damping parameter. If it is, if I put 0 here, so it has become simple harmonic equation. But here, the something, so it is damping parameter, we can say damping force. I'm going to write here damping parameter. And this one parameter. And this one, the right hand side, is general equation of SHM. Okay. General equation of SHM oscillator, or either you write SHM oscillator or either you write directly SHM, simple harmonic motion. Is this clear or not? Dx square upon dt square plus dx by dt omega, or in something so and so, that equation you remember or not? First of all, tell me this. Or should I give you the SHM equation first? Tell me, everyone. You remember anything, something? What is SHM? Or should I give you? Okay. Simple SHM equation for when a pendulum is hanging with some mass, or you can say spring mass system. When a mass is attached with a spring, so there is a force, is going to be a spring force. So that is going to be mass into acceleration. That is going to be minus k of x. Acceleration is going to be d square x upon dt square. So then it is going to be ma instead of ma d2x upon dt square plus k of x equals to 0. Okay, beta. And then this d2x upon dt square plus k by m equals to x. Okay, so the k by m I can write equals to omega square. So this is my general equation for SHM. D square x upon dt square plus omega square x equals to 0. Okay. If I apply force or this thing, this is my forcing parameter or this is damping parameter. Force equation, this dq by dt. Okay. Is this clear? Instead of x, instead of displacement, I replace charge simply. So I hope and I believe now this d square q upon dt square plus q by lc. This is the simple general equation, and this dq by dt r and this vm sin omega t is you can say a damping parameter. No? Force SHM. This one is forced. Is this clear? Just type everyone yes if it is so. And if I need to explain again, so please let me know. Clear na? Good. So now the equation of this general equation is this. Q equals to Qm sin omega t plus theta. Differentiating both the sides with respect to time, dq by dt is Qm cos omega t or Qm omega cos omega t plus theta d2q. I mean again differentiating this. So we get minus Qm omega square sin omega t plus this. Substituting substituting these value in equation 2. This is my equation 2. So it becomes now equation 3. Okay. Here the capacitive reactance Xc is going to be 1 by omega c. Inductive reactance is going to be omega L, and the net Z, the net impedance of a LCR circuit. So that is not properly written. Wait. First of all, I need to write this. So much typo is going to be there. R square plus XL minus XC to the whole square. Okay. And that is going to be the under root thing. This is the perfect thing. Okay. So when we put this thing, Vm equals to sin omega t, Qm omega r cos omega t plus Xc minus XL sin omega t plus theta, and where Xc is 1 by omega c, XL is omega L, net impedance r square plus XL minus Xc square. Substituting this value in equation 3. So we get this Qm omega r by z cos omega t, and this rearranging the term, consider r by z is a cos phi. And what is cos phi? Cos phi here is a this phase factor or phase value, what we find in the previous class. Okay. What is cos phi here? We discuss this particular thing, r by z. Phase factor, or what particular name? Phase angle. Cos phi is phase angle, right? You remember everyone? In the previous class I given to this. Is this clear, everyone? Phase value, till phase value Okay. So the moment we put XC, XL and Z in this equation 3, so this converting into the equation where R by Z, we can write it down cos phi, or you can say consider taken as R by Z is a cos phi. This one is our phase angle, and in the same way, this one is our phase angle for L and C. I mean, this is the phase angle for resistive circuit, and this is the same phase angle for inductive circuit or capacitive circuit. For inductive or capacitive circuit. Okay, so putting this, dividing the two equations, I mean the whole, both this equation, sin phi and cos phi, C and D. Dividing this above two equation, we get xc minus xl divided by r equals to tan phi, and phi tan inverse xc minus xl by r. See, that is going to be very important, and in the coming slides you are going to understand why so and how so. Okay, substituting the above values in the equation 4, Vm equals to sin omega t, Qm omega z cos omega t plus phi, theta minus phi. So comparing LHS and RHS, comparing LHS and RHS of the equation, we get Vm equals to Qm omega z, where Qm omega is Im. Okay, because omega is not but 2 pi by t. Clear? And if I put Qm upon t, it gives me Im. Im stands for maximum peak value. Is this clear, everyone? Okay. So instead of this, we can write directly this one. This one. Like if you remember when we find the current for this inductive circuit. So I is given by omega into, not for capacitive circuit. So that is omega C into Vm, and then it is going to be sin omega t plus phi. Okay. So that particular current, that particular current we find for capacitive circuit. The same thing we are following here, where Vm where Vm into omega C can be written down Im, okay, wait, Vm upon xc, where xc is 1 upon omega c. Okay, and then it is Im. Is this clear, everyone? So in a same fashion, whenever we put every particular values from the previous slide, from this particular slide, from this, this is your equation 4, from this slide or from this slide, when we put these particular values in equation number 4, so I get this equation, and comparing LHS and RHS, I can get this Vm, okay, equals to Qm omega z, this one, because I can put sin omega t into cos omega t also. How so? Sin pi by 2 minus theta equals to cos theta, right? We derive this thing. I can give you this thing in the previous class so many times. So you can watch the previous class and go, get it, how we get this. So Vm, you can say magnitude wise, comparing LHS, RHS of this particular above equation, Vm equals to Qm omega z, and I can write Imz. Clear? Im, I already write it down. How we can find it? Im is omega into Qm, because omega is 2 pi by t also. Or even if you write 2 pi f, f is 1 by t. Is this clear, everyone? So how we can get this? Moving ahead, the current in the LCR circuit I dq by dt or I qm omega cos omega t plus theta. So I equals to Im cos omega t plus theta, where qm omega Im. Okay, I already tell you this thing. Theta minus phi is pi by 2. So you can put theta equals to minus phi by 2 plus phi also. And in this manner, when we put this value, so it becomes I equals to Im sin omega t plus phi. Okay, I am doing very fast, I think so, in this way. Till now, everyone is clear. Everything. Clear now, everything. I am just rearranging and putting the given values, what we already have. Clear? Beta, please turn on your cameras first of all, because I cannot see you, so how can I understand are you getting or not? And when I am on this particular panel where I can see you, I cannot see your chats. Is this clear, everyone? Okay, I'm starting from the very basic, very beginning. See, first of all, what we are doing, we are trying to find the current in this, or when we get the current in this particular whole thing. Okay, first of all, we need to find the current in this I. So how we can find the current in this? Because we know this only. We know whenever we apply any component in series, so the voltage is going to be divided. So using KVL, I can do that. This is my applied voltage, and the voltage is going to be divided into these three forms. I do that. Is this clear till now? This is my equation first. Now I want to find I, current. So instead of voltage drop across resistor, voltage drop across capacitor and self-inductance, I put it into the form of I. But then I put it into the form of I can find the basic unit here is Q, not I even. Clear, everyone? Because voltage on a capacitor is not in the form of I, it is in the form of Q, charge. So I need to convert everything into the form of charge to find the induced charge, or you can say to find the charge into the form of this omega t, or you can say alternating charge. Then I do this mathematics. I put di I equals to dq by dt, di by dt equals to d square q by dt, put into the formula again. Then we know it is a kind of a force equation. Force equation for what? Force damping equation. Okay, what we already done in the previous class, 11th class. For that, the answer is, for that, when we put when we apply a force damping, so the x equals to xm sin omega t plus theta. This theta is you can say forced parameter, and that Vm is the damping parameter. So we differentiate again and everything and put it back into this equation number 2, this one, because I need d2q upon d2 square plus dq by d2, sorry, dq by dt. When we do this thing, okay, till now equation 3, we put back everything in this. Obviously here one step is skipped, because xc and xl, how it comes, because they get into the terms of 1 by omega c and omega l. So directly, instead of writing 1 by omega c omega l, we put into the xc xl form, and net impedance z equals to this one. Substituting the above values in the given equation 3, this equation is going to be turned down in this way. Now this is the crucial thing here. For phase angle, how much phase is going to be changed on this particular resistor only, that is going to be given by cos phi, and on the inductive or capacitive both, because in the previous class I explained you, in the inductive circuit, in inductor only, my voltage is going to be ahead. What is the meaning of ahead? Wait a minute. Suppose in this current, okay, my finger is going to be visible. If current is going to be in this way, so the voltage is going to be in this way, ahead. This is the black pen is the voltage, and the finger is current. Okay. And if it is in this way, so now you can see the current is going to be ahead and the voltage is below. So voltage is going to be below the current, or before the current in capacitive circuit, and it is going to be ahead the current in inductive circuit. So that is, from there we get this find you can say phase angle, then dividing the whole equation this, I mean from the previous, first of all we find phi only, tan inverse this, and put it in the equation 4. So Vm equals to sin omega t, this, then after that just LHS and RHS equating thing, and then when we find Qm, okay, this one Imz, so I equals to dq by dt, and then again I equals to Qm omega cos omega t plus this, and then again rearranging the formulas and this particular thing. Clear everyone? So till now we are just trying to find the I instead of terms of terminologies of theta into the terminologies of omega t and phi, because phi we know phase angle, Im we know, and omega t we know. Here Im is Vm by Z, and Z is again this R square plus XL minus XC square. That is wrong written here. Here the thing is going to be negative. Now it is correct. Where phi equals to 10C, XL minus XC, that is also reverse. Okay. Instead of doing this again and again, now it is not going to be very. Thus, for theta equals to 0, as a result, the applied voltage and instantaneous current are in same phase. R in phase means same phase. For theta equals to 90 degree, the voltage applied is out of phase with the instantaneous current. Is this clear, everyone? So the main thing is this Im, which is Vm by Z. Z is this, theta, and phi is this. Sir, can explain again because I get low network problem. Again, I need to explain to you. I explained again, I mean already twice. Sir, I asked long. Okay. Okay. So in this way, we can find I equation, Q equation in general. This formula, this thing is very, very important. Directly they ask R, directly they ask Im, magnitude, or you can say maximum value in LCR circuit. Directly they ask phase angle. This is your phase angle for LCR circuit. Okay. Here phi, this one. Phase angle for series LCR circuit. Obviously, omega is given, L is given, C is given. So once you have omega, you can find omega XL. You can find XC. Obviously, it is a LCR circuit, so LCR, everything is given to you guys, and omega is given to you. Omega, other frequency. Is this clear, everyone? Do that in a series resonate LCR circuit. Okay, what is a resonate circuit? Resonate circuit, I don't think so till now you know. So resonate circuit is a kind of circuit where X equals to XL. Okay, now I think you know. Because resonance of a LCR phasor diagram and everything is after this solution. I mean after this particular two things. Okay, I give you one hint here, or I can give the solution because resonate is not taught you till now. Wait, calculate the impedance. Next question you can do by yourself. Resonate I can. You explained. Yes, but I need to. Okay. So in what it is given here in a series resonate LCR circuit. So there is a LCR circuit, but a resonant circuit, what it is. So resonant LCR circuit is the circuit where XL equals to XC in any manner. Clear? Simple. Or you can say the circuit is only resistor. You can also say that. There are so many names: resonant circuit, only resistive circuit, for LCR circuit. I mean LCR is connected in that manner, or you can say the voltage is applied in that manner, or either omega is applied, frequency is applied in that manner. So XL equals to XC. Now what is XL? XL is omega L and XC is 1 by omega C. So from here what I can find, omega square equals to 1 upon LC. Clear? What is the basic role and use for that? As we know, omega is what? 2 pi f. Is this clear, everyone? Omega is 2 pi f. So I am doing the square of this, which is 1 upon LC. So beta, this frequency is known as resonance frequency or natural frequency. So I can write F naught. So F naught, or sometimes writing down in this way, V naught, is nothing but 1 upon taking square root of both sides. 2 pi 2 pi f LC. So this is the main thing for now. Now what it is, what they ask in this, in a series resonant circuit, if L is increased by 25% and C is decreases by this, so how much resonant frequency will be going to change? Clear, everyone? Clear na? Means this is my resonant frequency, F naught. Basically resonance frequency, this is known as resonance LC. So this is beta your resonance frequency. So now if I change my L, if I change my C, so obviously 2 pi is a constant thing. So how it is going to be changed? That you need to tell me. I think now you can do that, but still I'm going to do for you. So resonant frequency V naught, okay. I already tell you how we can find this one. In this question, what is given? L prime, because it is increase. So L plus 25%, which is L plus L by 4. So it becomes 5L by 4. C decreases. So C prime, C minus 20%, which is C minus C by 5, which is 4C by 5. So when I do that, V naught prime 1 upon 2 pi under root L prime C prime, putting the value of L prime C prime, I get the same thing. So it is not going to change at all. Simple. Clear, everyone? Is this question clear to everyone or not? Everyone. Resonance circuit, a kind of a circuit in which XL or XC is going to be equal. It is also known as purely resistive circuit, because when I do that, so I can get Z, which is R square plus XL minus XC. L and C is going to be look like same thing for me. XL minus XC whole square under root square. So if my XL equals to XC, so Z is going to be R. So that is also known as purely resistive circuit. I teach you whole thing for resonance here. Clear, everyone? For purely resistive circuit also I can find this, because resonance circuit is XLX equals to XC, and the moment I put this, so Z net impedance, which is for LCR circuit, it is going to be R only. So from this I can get which color I took, tell me. Z equals to R only. So that is why it is known as purely resistive circuit. CKT stands for circuit. So the moment I find this formula, I put this things V prime, sorry L prime C prime into the V naught prime, I can get the same thing. Now this one is very easy. You need to find the Z only. A 204 a 240 volt 50 hertz AC supply has applied to a coil of this inductance, resistance, and capacitor. Find the impedance. And I'm not going to tell you the formula even. Everything is given. Okay. So here I'm going to take a break. Meanwhile, in the break, you solve this, and then I'm going to teach you important things related to resonance. Clear, everyone? Frequency is given, so you can find omega 2 pi f. I'm not writing, I'm just telling you. If you get omega, so you can get XL, omega L. If you get omega, so you can get XC, 1 by omega C. R is directly given. Find the net impedance under root R square, XL minus XC square. Okay. And there is a, okay, find this and then I ask fun question after this. Not fun, one question. What beta once more, new student? Yeah, Pavanji. I mean, what you want? Should I explain this again or should I need to tell you again? Frequency is given. This is your frequency. So you can get omega 2 pi f. Once you get omega, you can get XL. This is your L. This is your F. Sorry, this is your C. This is your frequency. This is your inductance. This is your C. This is your R. LCR. Previous question. Um, okay, after the break, I can explain again. Okay, do that first of all. Hello, hello, hello. Am I audible? Hello, everyone. Am I audible? Am I visible? Just turn on what I'm saying. Turn on your cameras or open your cameras. Yeah, that is a good word. Open your cameras, mute your mic, everyone. And yeah, so beta Pavan, whatever you ask, we are going to define again in the next slide. But I just tell you a kind of a circuit in which XL equals to XC. You can say impedance on inductor is equal to impedance on reactance. Basically, on inductor is equal to reactance on capacitance. That particular LCR circuit is known as a resonant circuit. So if I increase my L 25% and I decrease my C, which is capacitance, 20%, how does my resonant frequency, and that is the resonant frequency or resonance frequency, that is V naught or F naught 1 upon 2 pi under root LC. Clear? So the moment I put L prime, C prime, I find it down, there is nothing changed. So frequency remains same. The next question is LCR circuit is given, frequency is given. Tell me the correct answer for this. Go ahead. Which one is the correct answer? Tell me, beta, everyone. Tell me. Did you find it or not? Anyone or everyone? Here I can see 1, 2, 3, 4, 5, 6, 7, 8. 8 or 9 students. B, C. Anyone else? D or A also? Okay. The correct answer is B. Here XL equals to omega L 2 pi FL. This one. This one X equals to 1 by omega C. 1 upon 2 pi C is going to be there. Wait. Wait. Something is wrong in this equation. Let me check it out. C is going to be 8 microfarad, na? So 1 upon 2 pi. But recheck this thing. 2 pi F and C. So 2 pi is correct. Then this is going to be under root. I mean not under root, in the divide. I can tell you the method and then you can find the correct one. So it is going to be 1 upon 2 pi into 50 and then into 8 and into 10 to the power. Yeah. And this is 1 into 10 to the power positive 6. So whatever the answer is going to be, put it in there and then find the answer. Okay. Even I don't know which one is the correct, but the B is not correct if I am not saying. Is this clear, everyone? Okay. Obviously, the given option is maybe not lie in the correct range also. Check it out. Maybe it is going to be. Okay, so check this one. The process is still same, but you need to check the answer. You need to check it once. Clear, everyone? Or should I solve it for you? It is going to be pi 22 by 7. Okay, do that because it take times. I can solve it out, but it take times. Clear na? This is the method. You can solve it out. Now, resistance and inductance in series LR circuit. Okay, what it is? In general, in the coming slides, we are going to find LR, LC. LC circuit is going to be in the next class. LR circuit, RC circuit, and the basic phasor difference between the given circuit. Okay. And what is phasor difference? What is phasor diagram? We are going to find in the coming slide also. So first of all, a phasor diagram for LR circuit. Phasor diagram is nothing but I explained this kind of diagram in the previous class. like there is a voltage, how much is going to be the voltage on L is going to be ahead as compared to R, because whatever the voltage is going to be given here, the same voltage, or you can say the current and voltage for resistance is going to be in a same phase, but for inductance it is going to be the change. Okay, and that everything I explained in the great detail in the previous class. So obviously if the current and voltage in this, you can say if it is a I current, obviously I instantaneous current, I not sine omega t or cos omega t, something so and so. So voltage at resistance or current at resistance is going to be in the same phase, where voltage at inductor and current and detector are not in the same phase. So overall phase is going to be changed. How much is that? Clear? That we need to find in different kinds of circuit. For example, LR circuit, for example, RC circuit, and in LC circuit. But LC circuit is a somehow kind of a pendulum condition in which conductor is going to charge, then it is going to discharge, and then your capacitor is going to charge, then capacitor is going to charge, and then conductor is going to be charged. So there is a kind of a oscillation going on of a charge in between L and C. So we find LC oscillation and transformer in the next class. Is this clear? Clear now what I'm saying? There is a L, one component, there is a C, one component. So one charge, another discharge, one charge, another discharge. So it is a kind of a pendulum in vacuum. Once you apply a charge, once you apply a force, so that is going to be rotate. Okay. In pendulum system, we apply a force. In this LC system, we apply a alternating voltage. Once we apply the alternating voltage, so the charge, because charge is the basic property, because charge can create the current. So charge in the form of current, or basically current in the form of charge, or charge itself is going to be oscillate in between L and C, and that is known as LC oscillation. Okay, that is I'm going to explain again in the next class. But phasor diagram for LR circuit. So what we are going to discuss, the sum of VR and VL cannot be put equal to applied EMF. Why so? Because it is going to be somehow more, somehow less. The phasor diagram is drawn in the figure, in the next figure. The vector OP represent VR, which is in the phase with I, while OQ represent VL, which is leads I by 90 degree. This, wait. This is LR circuit. This is your OP, and so this is your XL. Wait a minute. This diagram is they eaten up. Okay, what is this vector thing? Wait a minute, I'm going to explain you. I can draw the diagram for you guys here. Just a minute. See, this is your one thing, this is your another thing. So suppose what they ask, phasor diagram in the shown figure, vector OP represent the VR. So suppose, wait. Suppose this is the given voltage. Okay. This is the given voltage, or EMF E equals to E naught sine omega t. So on the same line, because R, or you can say voltage at R is going to be the same. So this is my given voltage V, which is V naught sine omega t. Okay. And this is OP vector. OP vector is beta the vector in which we have VR, because VR or V is going to be in the same phase, but if I need to wait. If I need to show you the 90 degree VL, yeah, it's good. Don't need to worry. Okay, so this is my VR and this is my V naught sine omega t. Wait. Yeah. So suppose here at this particular axis my current is going to be I. So the voltage at inductor, where I can find the voltage and inductor here. Clear everyone? So beta this one is, you can say, OQ. This is your O, this is Q, and this is OP. So OP vector, okay, Let's do this in the same color. OP vector is basically the vector which is going to give you the voltage at resistance, where OQ vector is the vector which is represent the voltage at inductor. Is this clear, everyone? So this one is the voltage at inductor. This one is the voltage at resistance, and it is the given voltage. Basically, the current is flowing in this direction at this I naught sine omega t plus phi. So phi is going to be for IL, it is going to be, for IR, it is going to be 0. For IL, it is going to be what? It is going to be 90 degree. Clear, everyone? So that is the scenario. Is this clear, everyone? Clear? Okay. So in this way, the resultant of VR and VL is the magnitude of OR vector. Net E is going to be, wait. This is ZL, this is R, this is XL. You can understand in this way also. And then VR, VC. Okay. I also think in this way. See, you represent in this way because then you are going to confuse. Instead of given voltage, just focus on this voltage. So here my I and R is going to be in the same. This is my VR, this is my VL, and this is the net EMF, or you can say net E instead of net EMF, net voltage of a circuit. Net voltage of LR circuit. Now it is clear. Is this clear? So why should what should I do? And why should I do that? Because I and voltage at resistance is going to be in the same phase. So same phase in this way, and this is going to be the net voltage. Clear, everyone? This is going to be my net voltage for this entire circuit. VL is going to be OQ vector and VR is going to be OP vector. This is my now OP vector. So this OA, ON, whatever the net EMF, net voltage we are going to find, that is my ON vector. Clear, everyone? Clear na? Because then if I am going to give you the net given voltage also, so that is something a confusing terminology. So in this manner, the resultant vector, okay, because it is given R, so instead of, but I need to put R then instead of. So now this the resultant vector, which is OR, is the net voltage of a, you can say magnitude of vector OR, which is E, VR square plus VL square, and that is E square, V square plus VR square plus VL square, I square, R square plus XL square. And when we finding the current in this way, so I is R square plus XL square. This is magnitude terminology, everything. So we know this I E by Z. This is the net impedance. Net impedance for LR circuit. Okay, magnitude wise, as we know, whenever in any particular circuit the current is flowing, so the current is flowing divided by the given voltage to the total net resistance or impedance. Here we say impedance, here we say resistance as a impedance because the components are different. The components can be inductor, the component can be resistor, the component can be capacitor. So instead of saying the terminology resistance, we are saying resistance, reactance, or capacitance, or you can say impedance in general. So that is the impedance, and when this is the impedance, so obviously then Z, which is the total resistance or total impedance of a LR circuit, impedance of a LR circuit, so that is in general, then automatically Z is going to be R square plus XL square. Is this clear, everyone? and I don't think so it is going to be problematic for anyone. Clear now? Clear? So the resultant vector of VR and VL. So this is my resultant vector of VR and VR, which is OR. Clear? So OR is E, which is net or total impedance or total EMF. So it is going to be under root V square plus VL square. And from this diagram, you can find it also. If I make a perpendicular here, okay. So if it is my VL, if it is my VL, and this is my VR, so automatically this I can find with the help of PT, OR, net voltage. Clear now everyone? And that is the formula. Is this clear everyone or not? Because that is important. Clear? Beta, open your camera everyone please. If you don't understand, let me know, because it is important thing. Instead of sitting like numb or a student who doesn't know, want to discuss anything, ask something or anything. Is this clear or not till now? Tell me. From the LR circuit is starting. Because if it is clear, so RC circuit is going to be very easy for you guys. Good. Okay. So again explaining, this is a LR circuit. LR circuit is a kind of a circuit in which we are just discussing about L and R. So obviously in LRR, the phasor diagram is going to be, and that is your phasor diagram. And the same thing we are discussing here. We are finding VR and VL separately, and then we are finding total I. Okay, and total impedance with the help of this. So with the help of this, we can get this. So total impedance for LR circuit is Z, which is R square plus XL square under root. And this is your phasor diagram. As you can see that. So that is your XL. I mean, this is the phasor diagram for, you can say, resistance on inductance or resistance on basically resistance. Your XL, this is your R, this is your phase angle, and this is your ZL. ZL is net impedance for LR circuit. So phasor diagram for LR circuit, the phasor diagram shown in the figure also show that in LR circuit, the applied EMF leads, and you can see that is your applied EMF on volt inductor. So that is your VL. Here we have VR leads the current I, or conversely, the current I lags behind the EMF E by a phase angle, which is phase angle phi, VL upon VR, I XL upon IR, I cancel. So that is simply XL by R. And that is important, even very important. Okay. So rearranging this, inductive impedance ZL in the LR circuit is the maximum, in the LR circuit, the maximum value of current is I naught, E naught upon R square, omega square, L square. Clear everyone? This is very basic. So phasor diagram for LR circuit, it is known that the impedance of LR circuit is represented by ZL. Okay, ZL, ZC you can use. ZL equals to this. Instead of omega, you can put into this value. The reciprocal of this impedance is called admittance. And now what it is? See, impedance is basically what? Impedance is kind of a opposance, or you can say oppose, like a resistance too, right? So reciprocal of that is resistance. Reciprocal of resistance is conductance. If we know, if you know still, or if you remember. So if you don't know, it's okay too. Like we have a conductance, which is you can say a conductivity, basically the reciprocal of resistivity, which is Simon or ohm meter, 1 upon ohm into meter. Okay, and that there is another thing which is conductance, 1 upon resistance. So in a same fashion, in a similar manner, the admittance means it is going to admit, it is going to pass through easily, and that is reciprocal of ZL, and that is important too. Because in numericals, generally for LR or you can say RC, sorry, for LR or RC circuit, generally they ask ZL or ZC or the phase angle in general, but sometimes to make a question or to make a numerical difficult, they ask admittance. Or at that particular moment, first of all, we don't even know what our admittance is. So admittance is nothing but reverse of, you can say, impedance for any particular kind of circuit. If you know the impedance, you can find the admittance. Is this clear, everyone? Clear now, everyone? Good. In a same manner, same fashion, we are going to find the for RC circuit. Clear? That is your resonance for LCR circuit. Instead of LCR, that is CR circuit. L is not there. That is for CR circuit. In a same fashion, we are going to for CR circuit. But the main difference, as you can see, in CR circuit or in RC circuit, the voltage at capacitance is going to be below, or you can say we're going to be lag, and voltage at resistance is going to be the same as current, or you can say same as the you can say where the current is going to be, or in general at the x-axis. So here the diagram for the previous is going to be tilted down, nothing more than that. Clear? So this is your resistance and capacitance are in series circuit or CR circuit, RC circuit basically. Phasor diagram for CR circuit, RC circuit basically. I mean, I have the tendency to say RC, and that is RC circuit. Current through both the resistance and capacitor will be same at very instant. Okay. And the instantaneous potential difference across C and R, VC equals to I XC, VR equals to IR, because they are in series. So I is going to be remain same at C and I is going to be remain same at R. VR is the same phase as this particular I. Okay. But VC is going to be lag behind by 90 degree. This is in this way because I is going to be in the same manner here, but VC is going to be 90 degree, and that is your total EMF for RC circuit. Real RC circuit. Clear, everyone? That is not going to be give you the same thing. Please, anyone tell me why we don't get the same? Tell me. No one asked me, so I am asking. Tell me. According to KVL, we need to get some same thing, isn't it? Then what happened in this AC circuit, specifically LR or RC circuit, like we apply this EMF, which is E equals to E sin omega t, right? In the previous case also, the LR circuit, this is my net impedance. Sorry, this is my net EMF on LR circuit. Here as well, I cannot get the same thing. I get this E square equals to I square R square plus X square. Or this is the thing here. This particular. This one. Hence VR square plus VC square equals to E square, or E is under root VR square plus VC square. Why not we get the same thing when we apply this? Tell me, anyone. You need to get it, isn't it? It's like you distribute 5 rupees into 2 plus 3, but 2 plus 3 doesn't give you 5. Isn't it? Why this is happening? Tell me if you know so, and if you don't know, so why don't you ask? See, I'm repeating this sentence again. Sorry. Maximum time. I'm saying maximum time, more than 95% time. Whatever the basic question, whatever the basic topic, whatever the basic thing you think na, like that is the most basic. No one is asked. Better don't believe me. More than 90% people don't even know this thing. This is very basic, na? Like when I apply something, so I need to get the same thing in the, you can say if I give you 10 rupees to divide in 5 students. So when I'm going to get back these 10 rupees, so the same thing I need to get, but that is not happening in this scenario. So why? What is the reason? Like I apply something voltage, I apply any particular kind of alternate voltage, and I get something else when I add it down on R or L, or when I add it down R or C. Why it is? Why it's happening? What is the reason? Have you think in this manner? Obviously no one. I teach in, I mean, since quite long, so no one bother about it. I don't know why don't you guys bother about it. The moment you start bothering about it, you start enjoying this thing. Basic thing. Okay, so the why, answer of why is very easy. See, this C is not, you can say your resistance or simple conductor. It is store charge. It is not store current. Clear? In the same manner, L is what? Inductance. It is not following the current. It is following, you can say, changing in current or changing magnetic flux. Clear? So there, in the transformation of energy, some energy is going to be lost. Clear na? If you transform your energy from one form to another, do that. Try that once, anytime. Like whenever you boil the water, if you precisely measure, some of the water is going to be converted into the drops of, or you can say droplets of water vapor, isn't it? So if you fill your bucket or if you fill your utensil, so few of the limit, or you can say very little amount of water is going to be removed. Where it is going? Where? Normally it is going into the phase change. The phase is changed because you don't know at which particular moment the phase is going to be changed. Obviously, the moment when the 100 degrees Celsius of each particular water molecule, water particle, but you don't know at which time it is going to be, because generally we don't know. So in general scenarios, in general case, that these all things happens everywhere. Clear? And that is why we did not get the same voltage or alternating voltage whatever we apply. We get something less. So why this less? This less because of in the conversion of kind of energy. Only in resistor, and that is why this voltage is lagging behind in this, and this voltage is going ahead in this. That is the, because current is changed into the magnetic flux term or magnetic, or you can say induced EMF, which is LdI by dt. Okay, and this is, I mean, to get current in this inductor, we need to differentiate, sorry, we need to integrate, because di by dt to get I, integration. So when you do the integration, so you have something which you are going to enlarge. And when you do the differentiation, when you have some large thing, you are going to differentiate it. So that is why voltage is lagging behind in this C, capacitor, because what is voltage? Q by C. Okay, and what is voltage in this EMF thing? And I need to get Q. So what is Q? dq by dt equals to I. So put into the form of I. dq equals to I dt. Clear? Clear now, everyone? So that is why it is happening here. Okay, back to the question again. So current through the both resistor and capacitor will be same at every different. Potential difference across C and R is this: VC equals to IXC, VR equals to IR. So hence V square R plus VC square equals to E square using this terminology. So E equals to under root V square plus VC square, and that is the same thing. Now the term R square plus X square represents the effective resistance of RC circuit and called the capacitive inductance, or you can say, sorry, capacitive impedance. So hence the RC circuit have a capacitive impedance ZC, which is R square plus XC square, and XC is nothing but 1 upon omega C. Okay. So the phasor diagram for this, okay, we done this thing now. That is repeat. It is not going to be bother. Now this is the thing we need to take care. So phasor diagram for CR circuit. So capacitive impedance in RC circuit terminology, this R square plus X square effective. A position offered by RC circuit follow AC through it. It is known as the impedance of this. The phasor diagram shows that RC circuit is applied EMF lags behind the current I leads the EMF E by a phase angle phi given by tan phi equals to VC by VR, XC upon R, 1 upon omega CR, 1 upon omega CR, and that is how you can find phi. So what is phi here? Phase angle in RC circuit. Okay, phase angle in RC circuit, and what it is going to be matter for in RC circuit current leads voltage applied on capacitor VC by phase angle phi. Okay, according to WCR, you can find this. Generally, it is 90. Front color. Wait a minute, beta. Okay. Generally, phi 90 degree. What is the meaning of saying that? VC lags behind by IC, or you can say I, by 90 degree. Okay, so that is the terminology. Clear, everyone? But it can be changed also. The manner, the moment I change my W is changed from frequency, given frequency, or C or R. Clear? In general sense, it is 90 degree, as you can see from the previous, this one. Okay, but mostly it depends on this omega and C and R. The same thing we are following. So the total impedance, net impedance for RC circuit is known as capacitive impedance. The total impedance for this particular kind of terminologies for LR circuit is known as this. Okay, and we are done for today. Yep. Okay, so now it's your turn. Do this assisted practice. Okay, for assisted practice I can explain you guys, but I'm not going to solve. The voltage applied to circuit is this 100 root 2 cos omega t. Draws a current this much. Taking the voltage as the reference phasor, the phasor representation of the current in ampere is. Tell me which particular option is correct. That's it. Phasor representation is what, beta? Phasor representation, you need to find the angle phi, and you need to draw the diagram also. So V is given, I is given. Okay, when V is given, I is given, phasor diagram. Okay, try this one first of all. And tell me which one is the correct answer. Okay, you need to find phasor angle, and then you need to represent also. So obviously representation you cannot show me, but at least you can show me the correct answer and give me the correct answer. Clear, beta? Do that. Or should I explain this? And if you don't know anything, so tell me right now, so I can explain this, and then you can do the next question. The next question is easy one, but again you need to draw the phasor diagram there also. But at least that is easy. I'm going to beta. Wait for a while. Pawan, where are you? I cannot see you. Wait. Okay. Try a little bit about it, and then I'm going to do that also. Meanwhile, I can find a class assessment for you guys. First of all, because it is going to be in next few minutes. Where is this? Just a minute, beta. Wait for a while. Six questions are there. And yeah. Should I explain? Are you trying? Anyone? Tell me. Okay, I'll explain. I think you take a lot of time and I don't want to. See, V is given, I is given. And here this theta or phi is also given. So we need to know what they ask. Taking the voltage as a reference phasor. Reference phasor means you need to take this voltage as a 0. So given that Vt is this much, It is this much, to consider voltage as a reference phasor, the first step would be make cosine as a sign. Not it is not sign, it is sign, because I need to take this as a reference. Okay, so when I make it a sign, so obviously how can I do that? Cos theta to sine theta, it is going to be sine theta plus pi by 2 or minus pi by 2 also. Basically sine theta minus pi by 2 is cos theta. So if I need to write sine theta, automatically it is going to be cos theta plus pi by 2. Got it? So same I'm doing here. I'm just adding pi by 2 angle. And then sine theta I can do that. So Vt 100 root 2 cos pi t is going to be 100 root 2 sine pi t plus pi by 2. Or you can do that sine pi by 2, I mean sine theta plus minus pi by 2 is generally cos theta. So we can do that. Is this clear, everyone? That is pure mathematics. It is going to be used here as well. Is this clear, everyone, or not? But please, everyone, open your cameras. I don't know why I need to say this again and again to you. I don't know why. I'm explaining you and you just turn off your camera. So how can I see you guys? How am I able to look at you like you are understanding or not? Obviously, your camera quality is very, or you can say, worst. I cannot understand like you are getting anything or not. And I think mine too. Okay, agree on that. So at least instead of nothing, let me visualize something. Like I can see your faces, I can see your like facial expression, like is it getting anything or not, right? So that is, we can do that. Why we are doing? Because we, I mean that is written in the question, we need to take as a reference. So obviously when we need to take as a reference thing, so we need to make equal both of things. So Vt is going to be this much, I mean cos into sine, 100 pi by t. You can say 100 pi is nothing but omega. omega t plus pi by 2. Okay, so that is Vt changed version into the sign terminology, and that is I given. Clear everyone? So now obviously if I need to find the phi, that is theta 2, so automatically phasor diagram from above equation can be drawn as this: Vt, which is pi by 4 ahead, It. As you can see, by considering voltage as a reference, current lag behind by 45 degree. Why so? Because as you can see, that is pi by 2 ahead, and that is pi by 4 ahead only. Clear? So the phase theta 2, or sorry, theta 1 minus theta 2, you can write in this way also, which is pi by, okay, I need to 2 minus 1. So that is beta theta 2 minus theta 1, which is pi by 4 minus pi by 2, and that is, it is going to be minus. Okay, so as you can see, by considering voltage as a reference, current lag behind by 45 degree. So RMS value of current in phasor form is IT, which is 100 root 2 by root 2, equal and less than minus pi by 4. So that is your this thing. Is this clear? So the option A is correct. Is this clear everyone? This one. Clear everyone or not? Okay. I can't do anything, sir. It's okay, but I'm not saying only to you. I'm saying in general. Is this clear everyone or not? Should I move ahead? Okay, now three currents I1, I2, I3 meet at a node which is okay, what it is in general, this is I1, this is I2, this is I3, suppose. Okay, obviously if I1, I2 is given, so I3 is going to be in this way if they are coming. So wait. Meet at a node. If it is meet, it is coming in. Wait, I need to, yeah, it is going to be coming then also. Okay, so at this particular node, the current is going to be 0 because every particular current is going to be here. So obviously from this particular node, the any particular fourth branch is going to be, which is not given. So whenever this condition is given, I1 plus I2 plus I3 or any particular meet at a node, so the summation of that particular current is 0. That is the thing I want to discuss first of all. So suppose this is I1, suppose this is I2, suppose this is I3. So at that particular for an instant, it is going to taken as a net current 0. Obviously, it is not going to be net current 0 because we need to follow this superposition of current, and that is going to be some fourth branch where the total current is going to be outside. Okay, is this clear now? But we take at this particular moment, this is node. So at this particular node, the current is 0. You need to tell me the I3. Tell me. Or should I explain this one also? See, one thing is very for sure, you can find it down in one particular current. Current is, you can say leading, because positive sign gives you this phi, and that is leading. And in one current, the current is lagging with the same angle. Clear? So now, after these two things, I3 is minus I1 plus I2. I1 you know, I2 you know. With the help of phasor diagram, find the R, resistance, and then this. This is basically more towards the vector thing instead of Okay, I can give you because I don't think so you're going to get what I'm saying. So how we can solve it? Let's see that. See, there is a given that the currents I1, I2, and I3 meet at a node from the above concept, we can find this. I already explained this. Since the current is given the phasor form, hence the addition of current I1, I2 can be done by using parallelogram method. So what is the parallelogram method? You are going to find in the next page. Don't worry about it. I1 is this, I2 is this. It is a given thing. So this is your thing. As I can say, I1 is leading behind or it is lagging behind 60 degree, and that is your reference point. That is I. So the phasor diagram can shown in this by using the parallelogram method. The net IR is nothing but I1 square plus I2 square plus 2I1 I2 cos theta, where cos theta is this whole angle 120 degree. From the equation 1, 2, 3, what is 1, 2, 3? I1 I2. This is your 1 or 2 na. So I1 I2. Obviously you cannot do that directly. So RMS value you need to find 10 square plus 10 square, because if I'm not wrong 10 is given, or maximum value in general. Okay. So then magnitude, since I1 and I2 has the same phase angle, as well as the magnitude IR equals to 10 sine 400 t ampere. Since the sum of all the current is 0, hence I3 equals to minus of IR, which is going to be minus 10 sine 400 t. Phase angle is not going to be there. Clear, everyone? Is this clear what is happening here? This is your I1, this is your I2. I mean, in the both case it is going to be, and I3 is going to be in this way. And they are going to meet at particular point where we are going to get the current. Is this clear or not? So for this particular, the correct answer is C, minus 10 sine 400 omega t. The correct answer is C here. This one, where it is. Is this clear, beta, everyone? Or should I need to explain it again? Tell me. Simple meaning or simple method when the any particular branches of current meet at a node. So at that particular moment, the current is going to be 0. For instance, not for every particular time. Here the current is given in the terminology of this same thing, sine omega t, sine omega t. So we make this particular diagram, and then with the help of parallelogram law, which is a vector addition law. Okay. So we take this, because obviously these are vectors. I mean, current cannot be taken as a vector, but in phasor diagram, we need to take as a vector the resultant current. And the resultant current is the negative of I3. This is your resultant current, IR, and the I3 is going to be in this direction. Okay. Is this clear, everyone? Or do you have any doubt, question, query in this question only? Is this clear, beta? Pavan Aditya, Shakti, Shrutika, Netra, Sai, Parikshit, Sudarshan. Okay, if you don't have. So this is the summary of this today's class. What we learn in this: AC voltage applied to a series LCR circuit, phasor diagram. Okay. In this, the most important thing is, you can say ZL, ZC, or in general Z. Z is impedance for LCR circuit. ZL is impedance for LR circuit. ZC is impedance for what? Capacitive circuit. In the same way, phi phase angle for LCR circuit, phi L phase angle for LR circuit, phi C phase angle for this capacitive circuit. Okay, and then main important thing, resonant frequency and resonant condition. So resonant frequency and resonant conditions are what? Omega naught 1 upon 2 pi under root LC. Okay, so these three things are the more important for numerical perspective. Other things are also important, but those are more theory wise. Is this clear, everyone? Is this clear, everyone?